This conference will now be recorded.
All right, so yeah, without further ado, I'm going to turn things over to Rebecca. So everybody, Rebecca Skinner. Thank you.
Are you all able to see my screen? First question,
Yes.
guys. All right. Awesome. So I'm Rebecca Skinner. Thank you all for taking some time out of your evening to come listen to me talk. Tonight we're going to go through an introduction to networking. So just a little bit of background. If you want to get in contact with me after this talk, I'm on Twitter at Cercerilla. I'm also on GitHub at Rebecca Skinner. And this talk will be on GitHub under the presentations repository. Uh, all of my talks are licensed Creative Commons by attribution, and all of the views that I'm sharing here are my own and don't represent the views of my employer. So the internets, right? We all have a thing or two to say about the internets. Most of us are doing our day jobs in a way that directly or indirectly involves the internet, networked computers. So if you work with software that depends on any two computers talking to one another, it's helpful to know a little bit about networking. And we're using the term computers very loosely here because networking and the idea of computers talking to each other is very broad, right? We have things like the web. Obviously, your web browser is talking to some server somewhere, even if you're just a single page application that's running entirely in the browser. You have to get that JavaScript from somewhere, or maybe you're a mobile app and you're interfacing with some backend service. Or IoT is a very network centric model of computing. Maybe you're working on video streaming or building data science platforms with distributed computation. All of these are things that involve computers or computer-like things transmitting data back and forth, one thing to another. So um, the problem is for all of the ubiquity of networking in modern computing, I find that it's one of the weakest areas for a lot of people that I work with. So most of my work these days is sort of software development adjacent. As a principal engineer, they don't let me touch the keyboard very often. I spend more time in meetings these days than writing code, but I spend a lot of time working with people and trying to help people really fill the gaps in their understanding of the systems that they're building. And uh, pretty consistently, networking is an area where people feel like they're a little uncomfortable. I think most people have a very superficial understanding of how networking works, but you get to talking to them and they feel just a little bit uncomfortable, right? Like there's this whole big world under there of all of this stuff that they don't really understand and kind of vaguely feel like they ought to know more about it, but they never um, quite do it. So I'm hoping that what we can do today is we can just kind of walk through that full stack of networking and really give you a very high level picture of how communication between these computers happens. And, we're going to touch on a lot of topics, and each of those topics is going to have so much more breadth and so much more depth that you could go into. And we're not going to go into the nitty gritty details, but I just want to introduce you to all of these different components that are involved in making the internet actually work and make it this system that is, I guess you could use the word functional to describe it sometimes. This really amazing, complex system that somehow still works. Um, so before we move on with the slide, I'm just going to pause and see if we have any questions or if anybody thinks that they don't work in a field that's related to the internet, I would love to hear it. Uh, and if anybody else has anything they'd like to share. All right, let's go ahead and move on. So a browser walks into an address bar and says, right? So this is, for most of us, when we think about networking, the entry point, the gateway to our networking is our web browser. And, we kind of know that we have this URL here, example.com, that I have up here in this web browser. And, we know that's like a server. And I'm going to tell my web browser, hey, take me to example.com, and it's going to do some stuff. And what is that stuff? So we have this like stack of things that's going on. So at the top level, we have our web browser. Um, that web browser is going to make HTTP requests and it's going to get back HTTP responses. And I think a lot of us, like a lot of you, have probably looked at what these look like. Like you kind of know, like what a get request looks like, or what a response is. We all know what like some HTML is going to look like. But to do that, well, how do we even know what to request or where to send that request? Well, we have to do DNS. We'll talk a little bit more about what DNS is. But if we want to do DNS, after we've done our DNS lookup, we want to go talk to this web server, we have to do a TCP handshake. So what's involved with that? And to do a TCP handshake, we have to get some messages to this computer in the first place. So we have to do IP routing. And if we want to do IP routing, the first thing that we need to do is we need to get our data to the routers. So we're going to have to do some Ethernet switching. And if we want to get some data to the switch, we're going to have to send that data out our computer. So we're going to have to do some socket code in user space to generate our request. And that socket code is going to go to our operating system kernel. And that operating system kernel is going to go to a device driver that controls our network card. And that device driver code is going to talk using DMA, direct memory access, to the memory on our card or over the PCI bus. And then that network card is going to generate some rising and falling electrical signals across twisted pairs of cables inside of Cat5 in a specific way. Or maybe we're generating RF signals for our Bluetooth or our wireless networking. So there's so much that's happening here. And we're going to look at some of this in just a little bit of detail. So a lot of you may have heard this the 7-layer model or the OSI model. I always think of it as the 7-layer burrito from Taco Bell. And it has like all of these layers, right? And you have like maybe a REST client and an application API, and I don't know, it's like turtles all the way down at some point. And like, so you have this OSI model, and then you have the TCP IP model. And the OSI model is the thing that most people, I think, are taught in school. And it's this very like ideal, formalized, like here's what networking is and how it looks, and here's the shape of it. And then we have the TCP IP model, which is like, here's some crap, and maybe it has some structure sometimes. I don't know. And one of those is realistic, and the other is the OSI model. because it does not actually end up reflecting the reality of how networks work in any way, shape, or form. So this is a good point to pause if anybody has any questions. If you don't want your voice recorded, you are welcome to type in the chat and I will read your question out loud. Cool. All right, so let's move on. So we have this like OSI model. What parts of it do we actually want to look at? Well, for this talk, we're going to narrow down on 5 concepts: DNS, TCP, IP, routing, and switching. We'll talk about a few other things as well, but these are the really the most important things to understand as we're trying to get a holistic picture of what's going on when we want to send a message from one computer to another. And we're going to start with DNS because most of the things that we're going to do on a network, at a high level, at a conceptual data flow level, DNS is our first step. Because DNS is the way that we translate a name, like example.com, to an IP address. So if you're talking to some other computer over the internet, right, these nice domain names that we pay all this money for, that we remember, that we bookmark, they don't really mean anything to the underlying internet infrastructure. These things really only exist in the domain name system. And so DNS is just a way to map these nice, friendly, human-readable names into a set of numbers. This is an IPv4 address. And so DNS is made up of a bunch of different kinds of records. And they all do a little bit. So if we look at some popular records, we got like A, Quad A, CNAME, Text, Abbey Road, very popular record. And if you own your own domain name and you go into the dashboard for your registrar, you're going to see these things pop up. So an A record is basically an authoritative record saying like this this address goes to this IP address, this like example.com, go here, and AAAA, the record, this is the same thing but for IPv6. The CNAME is like the canonical name for a given resource. This is like here's like the real like identity of this thing. TXT is some like miscellaneous information. So and then there are some others. There's like MX, which is how you MX or mail records. So if you want to send emails to somebody, your email may be hosted in a different location than like your web service. So, and the way that you send email is going to be a little different. So we have these MX records. So all of these records are just different ways that we can map a domain or a subdomain to some address. But we don't have like DNS servers that know about every address in the world because that would be a lot. There are a lot of addresses. So DNS is hierarchical. So if you think about, like if we go to example.com, right? Like we might type example.com, but the actual address is example.com dot. That final dot there, we tend to omit it, but in the world of DNS, that's the root. So if you think of each dot as sort of going down a level in this hierarchy, so we have the final dot there is the top of this hierarchy. This is like the end of the line. And so we're going to go to com. And so we have a COM DNS server, and this is like what we call the root DNS server. And then below that we have like example, and so example, there may be example company that sells examples, owns its own DNS server, and so the com is going to say like, well, example is authoritative. It's really in charge of those records. And on the other side of the internet, when you're setting at home and you're looking something up, you're typically going to go to either a DNS server that's owned by your internet service provider, or maybe you're using like Cloudflare or Google's DNS. And those are what we call recursive DNS servers. So they don't actually own any like authoritative mappings between domains and IP addresses. What they're going to do is they're just going to go look up something on your behalf, and they'll probably remember it for later. So they're going to cache DNS entries. So you kind of think like what's going to happen is we have these hierarchies, and so you're going to go to a recursive DNS server, and it might go to a recursive DNS server, and then it's going to go to some DNS server that it knows about, and like maybe the root servers, and then the root servers are going to say, well, I know that the authoritative server for this belongs to this registrar, and then that registrar is going to say like, okay, here's the final mapping. And so you go through like 17 layers, and at the end you successfully downloaded that tracking pixel that is going to tell you to buy the same shoes that you bought last week. So I just really like this image, so I'm going to stop here and ask if anybody has any questions.
Can you guys hear me?
Yeah.
Yep.
Yeah, Rebecca, I just wanted to ask you really quick. Of all the records you mentioned, I know what 5 of them are, and you cover 5 of them. The only one I don't know what it is the Abbey Road. I was wondering if you can
That's
let
a
me know.
joke.
Oh.
That's a joke. It's a
Oh
Beatles
my
album.
God. And this has been recorded.
It's okay. I was going to ask the same thing.
That's a really good joke.
It is a good album. It's a good record.
A very popular record.
Yeah.
Any other questions?
Yeah. So subdomains, they get their own IP address, right? Is that IP address at all related to the original domain's IP address, or is it just two random IP addresses and they're somehow, I guess, just kind of linked otherwise?
They can be. So you can say, for example, like www.example.com, it is it like for that C example.com, right? So you can redirect through DNS, or you can just say like these are both pointing to the same IP address, right? You can point as many domains as you want to the same IP address, and
Okay.
in fact that's very common, right? Because if you think about cloud infrastructure, a lot of times what you're going to have is you may have like a thousand domains or subdomains, and then they're all pointing to the IP address of maybe uh, this. And I should say it's not necessarily one IP address, right? I can say like I have these 5 addresses that are associated with this domain, and you can go to whichever one you want. And typically what's going to happen is you're going to round robin between them if you're doing multiple requests. And so maybe those are the 5 IP addresses of some shared load balancers, and they're serving maybe 1,000 websites, but they're going to look at the host header in my HTTP request to figure out then what internal address to map that to.
Sure.
So you end up with this kind of like hourglass thing, right? You have all these domains, and then they're all going down to like these few IP addresses, and then they're all fanning back out to all these cloud instances.
Cool. Thank you.
Any other questions? All right, cool. So let's go on to the next step. So DNS is great. It tells us where we're going to go. But the next question then is, how do we get there? So I have some IP address, and I want to get there. And usually, when you're talking about sending some data uh, to somebody else, you're talking about like TCP or UDP. Those are the two main protocols that we're using on the internet. Um, and you can think of these as a way of multiplexing uh, data across like a single IP link. So, excuse me. So if I have two computers, they're connected, they're sending data. That's just like one big stream of data. But logically, I probably have multiple things that I want to do over that link, right? Because I might want to serve a web page over that link, but I also still want to be able to get software updates, or I need to be able to accept SSH or whatever. So a whole lot of stuff needs to all share that same IP link. So when we're doing multiple things over one link, that's multiplexing. And so typically TCP and UDP they're providing ports, and that's the sort of base unit of multiplexing. And there's IANA, that's a standards organization that's responsible for defining like all of these ports that we used to use before everybody just started shoving everything over HTTP anyway, because everything else was blocked by corporate firewalls. So we're kind of back to square one in a lot of ways there, unfortunately. Um, of the two, TCP and IP, I would say most traffic on the internet uses TCP. The caveat there is right now, like most traffic on the internet is probably people streaming Netflix, and Netflix is UDP. So maybe this slide is actually incorrect, but TCP is really like this is a way of sending data, and you really want to try hard. You want to make sure that it gets there. Um, some of you may have heard this term, like the three-way handshake or the three-way like hand wave from at least 6 feet away while wearing a mask. But this like three-way handshake that TCP does, and then a lot of the other ways that it works, it's really about um, two fundamental problems. The first is if I'm sending you some data, how do I know that you got that data? Because the internet is pretty unreliable, right? Like I can like have my wireless might go out because my neighbor started to use their microwave, or like the bird got distracted that was carrying my message in its claw, or the backhoe operator dug through the fiber optic cable. Like there are an enormous number of ways that things on the internet can go wrong. And if I'm sending you something important, I'd really like to know that you got that message, and you would really like to know that you got the entire message, right? If somebody's transferring some money into my bank account, I would really not want like those last three zeros to just disappear because that packet loss happened, and all of a sudden my employer is paying me like $1 this week. I would be pretty unhappy about that. So TCP gives us a way of making sure that the data that we're sending has integrity. We know like how much data we're sending, what the order of that data should be, what the checksum of that data should be, and I'm going to know that the person, when I say person, I mean computer, but computers are people too, that the person on the other end has received that message. The other thing that TCP does is it makes sure that we're sending data in in the right amount. It does what we call flow control or congestion control. And so the idea is, we want to send and receive as much data as we can without actually overloading one of the computers on one end or the other. And if we try to send too much data over a signal that can only handle a little bit, then we're going to be worse off because we're just going to be overloading our connection and dropping data left and right, and it's going to be slower than it would have been if we just slowed down. So TCP uses congestion control algorithms, which are really interesting. I'm not going to go into them, but there's some really interesting science behind the way the flow control algorithms work to try to negotiate the speed at which we send data. And then the ISPs completely screwed all of that up by adding huge buffers to cable modems, and now the internet is a worse place because they wanted to make their internet seem faster. That's called buffer bloat, and you can read some very opinionated articles on why this is a problem. And that's also interesting as well. On the other hand, we have UDP. So we have a funny UDP joke. I don't care if you get it, because that's pretty much the way UDP works, right? It's just like, here's some data, here's some data, here's some data. And, in a lot of cases, this is fine. So video streaming, right? If I drop some data in my video stream, I really don't want to pause the whole video stream. I really don't want the office to pause every time I lose a packet. Just degrade the video signal and let me go back to watching Jim prank Dwight. I'm going to be happy. So UDP is for data where you really like recency is far more important than completeness or absolute accuracy in the data that you're sending. Because of that buffer bloat problem, another thing that you'll see is many applications now are starting to basically build little bits of TCP manually on top of UDP. So the application might say like, well, I really do care if my messages are in order, but I don't care if you missed a little bit of data. Just like, if I send you something out of order, only show like the most recent thing. So if you think about the video streaming example, right? Like, I don't care if I drop a frame or two out of that 24 frames per second video, but I do care that you don't show a later frame, an earlier frame if I sent them out of order. Or, for example, like a lot of online games, right? They want to know that certain data actually was received by the server, right? So, like I scored the points. I want to make sure that the server knows that I scored the points. But I'm sending very little data, and I don't want to worry about congestion control and deal with buffers. I just want to know that my data actually got there. So you have a lot of people sort of reinventing little bits of TCP on top of UDP in that way. But TCP and UDP, again, they let you send all of this data over an IP link, but they still don't know how to get anywhere. We have this IP address that we can send things to, but we still need IP. So IP is the internet protocol, and more or less everything is using IP on the internet. There are some other protocols that are used mostly if you're talking about like the core internet infrastructure or connecting data centers, things like that. There are some other protocols, but IP is the thing that we really care about when we're talking about networking. Actually, I'm going to stop here and open it up to questions.
I don't see any in the chat. I will say I like your definition of your explanation of UDP. That really helped me. That's very cool.
Awesome. All right, so let's dive a little bit into routing. So we you can think of an IP address like a post office box, right? So it's your address. It's your IP address is where computers on the internet are going to go to send you data, and they're going to do that through routers. And so an IP address is like a PO box. A router is like an electronic device that uses protocols like BGP to efficiently generate compact representations of sparse mappings between networks. Um, a whole lot of words because routing is kind of complicated. Um, Ultimately, what routing comes down to is another one of those games of telephone like DNS. When I want to send a message to another computer, I'm going to go to my router and I'm going to say, I have a message for 1.2.3.4. And the router is going to be like, can do, friend. I will get that message to you. And then it's going to look in its data set and it's going to be like, who the hell knows how to get to 1.2.3.4? Like, quick. Hey, I got something for you. Send it along, right? And so the routers are just going to do this until eventually one of them actually knows how to get the message across. Um, and like fundamentally, that is routing. Um, Routers are looking at just a very small bit of the overall message payload. They're going to look at the IP address, a few other like flags inside of that data set, and that's pretty much all they're going to do, except screw things up. Oh, they're really good at screwing things up because they're going to send your data, right? But they're not going to send the data that you sent. They're going to chop it up into small bits, send it in the wrong order, send half of it to this guy and half of it to this guy. Like it's a giant mess. But thanks to things like TCP, you can put it back together on the other end, and it mostly works. Mostly. When you, if you ever find that you have like 10% packet loss, you can think a router somewhere that got busy and just decided to drop like 10% of your packets on the floor because it was more interested in doing other things. So this is routing in a nutshell. Um, One thing I forgot to put a slide in here on is when a router is forwarding data to another router, you might wonder how does it know who to ask to send the data to? It can't just send it arbitrarily. You want to be making forward progress each hop. So if I have a message for 1.2.3.4, I might not know how to get it there, but I want to at least get it to somebody who can get it there and who is closer to it than I am. So I don't want somebody to say like, sure, I can get it there, but then end up like sending it through some wacky path that gets it back to me. And then I'm like, okay, well then I'm going to go hand it off to this other guy. Like that doesn't work. So there are these protocols called routing protocols. And the one that most people would be concerned about is called BGP. It stands for Border Gateway Protocol. And it's the protocol that basically allows routers to exchange amongst themselves a list of all of the things that they know how to get to and how long it will take them to get there from where they're at. And so this is basically routers, sort of the whisper network of all of the routers sending data. And what's absolutely horrible about this is it's primarily trust based. And so occasionally you'll have somebody like accidentally put a typo in the router and then like all of the data for, going between your office in St. Louis and, the server in Minneapolis is getting routed through like, China or the Netherlands or something because somebody had a typo in the router. And that literally has happened. And like it was probably an accident, maybe. Um, and yeah, so that's fun. There is some work on securing that, but it's still a little bit of Wild West out there in some places. So routing is how we get data from like one network to another, but we're not really like having routers like router devices involved with all of the network data that we're sending because a lot of times we're just sending data instead of like our own personal network, right? Like if I want to if I want to SSH from my laptop to my spouse's laptop for some reason, or I want to airdrop some files from my phone to my iPad, right? That's not going over the internet, but all of that's still built on top of IP. And so the way that that works is we have this idea within IP of these things called subnets. And so you can think of a subnet as a way of like partitioning all of this like set of IP addresses that exist in the world into these little like fiefdoms, right? So I have my own little corner of the IP address space that I'm going to do with what I want. And usually we're using these reserved subnets that have been set aside specifically for people to use like for their private networks. So if you have an IP address and it starts with 10 dot something or 192.168, those are private subnets that are considered non-routable. So you're never going to have to worry about that trying to go out over the internet. Um, but within a subnet, right, like how do you get packets from one device to another? Because routing is all about sending stuff from one network to another, but I want to get stuff from one device to another. And so that's when we bring in switching. Before we go into switching, does anybody have any questions about routing?
I guess kind of a question, but I guess an observation. I remember studying for one of the AWS certifications a couple years ago, and dealing with the cider blocks and all that. I just remember being really confused as far as I think the /16s versus the /32 versus the /8s. I can't remember if those are the right numbers, but there didn't really seem to be a rhyme or reason to it. It seemed like, but I'm sure there is, and I just missed it.
Oh yeah, let's dive into that. So there are two ways of writing what we call a net mask, and so a net mask is the way uh, that we talk about what part of an IP address is like the addressable portion and what part is like the subnet. So if you think of like all of the computers on my network might be all like 10.97.43 something, where that
Okay.
dot something is part of my network. So the way that we would write that is we would say like the net mask notation would be 255.255.255.0. Or if everything was like 10 dot something dot something dot something, we would say 255.0.0.0. And this, like, 255 might seem kind of weird, but that's all ones in binary. So 255.255.255.255 is 32. One is like 32 bits, all all true. So it's just one,
Okay.
like, right. So the slash is the other way of saying like how many ones. Because if you think of it as always going left to right, right, 255 is an 8-bit number, all ones. So if you think of from left to right, the first 8 are all ones, that's a /8. If the first 16 are all ones, that's a /16, or a /24, and so on. And the reason that we do that is because, like all this routing stuff, right? It happens like there's a lot of traffic that goes over the network, and these packets are small, and we're sending a lot of them, and we need to very quickly be able to figure out where things go. So if I want to know if something's part of the subnet, my local subnet, or if it needs to go to a router, right? I want that to be as fast as possible, and so I can actually just do a logical and. That's a single CPU operation to find the intersection between this address and my subnet, so that I can tell if something's within my subnet or not. And so a lot of this stuff, it seems kind of odd, but it really makes a lot more sense if you consider that it's all designed to be like very easily encoded in hardware and able to run very, very quickly.
Yeah.
Another peculiarity is that if like working in JavaScript, right, you don't really have to think about this stuff. But if you've ever dived into this idea of endianness, you have these computers and they operate in two modes really: big endian and little endian. And there's also this thing called middle endian. And the term came from the book Gulliver's Travels, where there were these two tribes, the big Indians and the little Indians, and they were at war over whether you should open hard-boiled eggs from the big end or the little end. And the term was picked because it's basically what order do the bytes go in a number that's stored in the computer, and is it left to right or right to left? And it doesn't really matter. It's a silly argument, but you still have to agree on it. So networking traditionally is all of the data in a network is stored in big endian format, but like an Intel processor is little endian. So one of those things that, like, if you're writing some JavaScript code, you don't really have to think of, but people that are working like in the kernel, they have to think of is like every time you get a network packet, before you do anything else, you have to like translate those numbers by rearranging the bytes to get it to something that actually makes sense on your computer, do all of your math, and then switch it back.
Thank you.
So that was a good question. Lots of answer for that question.
Yeah.
Anything else anybody's curious about?
When you talk about switching, are you going to talk a little bit about how AirDrop works? Because I'm just kind of curious.
I am not going to talk about that because I have no idea.
Fair enough. I'll look it up.
I'm glad it does though. All right. So switching. So when we talk about switching, we're talking about Ethernet networks. So we're no longer talking about IP addresses. Within your local network, we don't care about IP addresses. We have like this whole other random damn thing that we have to learn about, because clearly DNS, TCP, UDP, and IP were not sufficiently confusing, nor were they enough layers of abstraction. So a home switch, like switching, it's like a roundabout. Nobody knows how to use them, but they're cheap. Um, Switching is the way that we get packets from one computer to another on a local network. And we still have the same problem, right? We still have to know which computer that we're talking to, because I have like an absurd number of computers sitting like within literal arm's reach of me right now. And if I want to send some data, I still have to know like which computer should I be talking to. So we have this other addressing scheme called a MAC address. And I would say don't quote me, but we're being recorded, so somebody will. I'm not actually sure if I'm right. I think this stands for like media access control or something like that. Um, it like I don't think that anybody really cares. It's a MAC address, and a MAC address is sometimes called the hardware address, and this is uh, some address that generally you're going to get one that ships with the network device on your computer. So your wireless card or your physical Ethernet card. You can change these, and people do. Like if you're at a hotel and you want to like steal Wi-Fi, you change your MAC out, you like sniff the wireless network, figure out somebody that's already connected, wait until they disconnect, and very quickly change your MAC address to theirs, and then the authentication gateway is going to think that you're still good, and you just continue using hotel Wi-Fi, or if you're very nefarious, you change your MAC address to the MAC address of the router on somebody's network, and then all of their traffic goes to you, and you do whatever nefarious things that you want to do with that traffic. And so these are little, that's called MAC address spoofing, um, and it's interesting to read about, but we'll just assume that we're using these things for good and as designed. A MAC address is how we talk to your computer. But then we again still have the same problem of, okay, well, I need to get a message to somebody, and I have IP addresses because all of my applications are written with IP addresses, but my Ethernet switch and my Ethernet cables only know how to talk MAC addresses. So how am I going to translate between this IP address and this MAC address? So we have this thing called ARPing. And so ARPing is basically going to be like, hey, everybody, and this is a broadcast message, so it's going to go out to your entire network, and it's going to be like, hey, I'm 1.2.3.4 at this MAC address, or it's going to say, hey, who is 1.2.3.4? What's your MAC address? And that's how it's going to generate the mapping between the IP addresses and the actual MAC addresses when you're working without a router inside of a local like Ethernet network. Questions about that before we move on to the next topic? All right, so gateways. So switching is great when we're talking about things that are within our local network, but at some point we're going to want to get out to the internet. We're going to want to watch The Office on Netflix or something, and we need a couple of things, right? We need to know where our router's at. I don't know about you, but I don't really want to look up the IP address of my router and type it in every time I want to get on the internet. I would like that to just happen for me. Similarly, DNS. I do run my own DNS servers, but most people don't. Most people don't really want to think about it. They would like it to just happen for them. And so how does that work? Well, we have this protocol called DHCP. And what DHCP is going to do is it is going to basically wait around when a new computer comes online. It's going to say like, oh, I don't have an IP address. Oh, I don't have a DNS. Oh, I don't know where to send all of my traffic. Somebody please help me. And your DHCP server, which usually comes with your home router. So, most of us have a thing we call a home router. It's like really a switch and a router and a DHCP server all in one device. And it's going to say, okay, use this IP address. Here's the IP address of your DNS server. Here's the IP address of the router that you should talk to. And that's your default gateway. And so then as part of that IP address, you're going to get a net mask. And what your computer is going to do is it's going to say, okay, anything that's within my subnet, I'm going to use, I'm going to talk to my bridge, my switch, and just go like use my ARP tables and go out and talk to things on my local network. And if it's not something that's inside of my subnet, then I'm going to go to a router, which is usually like your default gateway. And I'm going to say, hey, can you get this to where I want it to go? And it's going to say, sure, I can do that. And it's going to send that message to your DNS server, which is going to say, here's the IP address that you wanted. And so you're going to say, great, now I have an IP address. Hey, router, can you say hello to this IP address over here? And that IP address over there is going to say, I heard you say hello. And then you're going to say, I heard that you said that you heard me say hello. And now you have your three-way handshake. And then you can start sending your HTTP requests. And that's really all I got. So any aggressive statements in the approximate structure of a question, actual questions, anybody want to tell me that I'm wrong?
I mean, I don't know if you'll have a great answer for this, so I don't know what the quality of the question is going to be. But so along that stack, I guess, is there a certain area or certain areas where you experience the most performance degradation, or where things really start to bog down, or does that just vary by each connection or whatever?
Yeah, so it varies a lot depending on the circumstances, right? Like I would say any given point could be a bottleneck. Um, buffer bloat is certainly a thing that's affecting the whole internet, and that can be a problem. But it's kind of a hard one to put your finger on because it's this like big systemic problem.
Sure.
A lot of times in home networks, you might have your routing speed sometimes can be an issue if you have like a lower end router, but now all of a sudden you have like 6 people all trying to stream Netflix and play video games at the same time. Just the actual speed that it can process packets and figure out where they go is a problem.
Sure.
Uh, if you're using your ISP's DNS, that's like the number one cause of internet outages. Is like, especially Charter around here, like their DNS is just like terrible. So you can like double your uptime just by using a different DNS server. So yeah, it depends. And the thing of it is knowing what the stack is, even if you don't know all the details about how everything works, gives you a lot more power to troubleshoot this because anything could be going wrong. But if you don't understand the stack, it's very hard to know where to even start looking.
All right. Yeah, I just upgraded a old Linksys router that I bought, I think in 2014. And I mean, the router that I put in isn't like top of the line. I think I spent like maybe $80 on the new one, but night and day difference. And I kind of knew that the little crappy Linksys was the bottleneck. But yeah, I mean, we were having all kinds of outages here, and no, we're not. We do use Charter, so things have been great, but that's just because the last 6 years have been so awful because of the Linksys router. So yeah, maybe
Right.
go ahead.
Oh, I was saying nothing changes the subjective experience of quality like bad expectations.
Yeah, the low. And I was serious. I was calling Charter just about every week and just going through the voice prompt, and I had that pretty much down to a science. And if I went 2 weeks without having a call, it was cool. They would just keep sending me fresh signals, and they would work. And yeah, just finally got sick of it. So yeah, Charter's a-okay now. But so here's just a weird question: if I'm local, if not Charter, who would you suggest?
I mean, right, that's the problem with ISPs, right? Like
Right,
most of them have a monopoly.
right.
Um, I think there's like AT&T fiber some places in St. Louis. We don't have it. We're in Tower Go South, and we don't have it here.
Yeah.
So I'm not really here to advocate for any particular ISP. Just I have found that Charter's DNS is particularly bad.
Okay. Well,
Yeah,
when the honeymoon's over, I'll maybe circle back with you.
if I can add something there, you did a great thing changing your router because apart from the fact that routers become old, like the electronics inside become old, you get dry cracks, that kind of stuff. It has a huge difference. And then later routers have different firmware. They're
Sure.
easier to update. They get new firmware pushed more frequently.
Yeah.
And obviously they also run on the latest bandwidths. So yeah,
Right.
unfortunately,
Yeah.
that's one of the things you have to constantly be upgrading,
Yep.
else you just fall behind the game.
Yeah. I can't remember the bands. I think we're using is it like 5 something or the other, where I think there's a 5 and a 2 maybe in the old router or 2.4, I think. We were using just 2.4, and I could be screwing these numbers up. And then now we have the option to go, I think 5.0 or something like that, and we're using that, and that seems to be making a really big difference. But yeah, thank you.
The 2.4 versus 5 gigahertz, a big difference there is the higher frequencies can support higher bandwidth, but they have worse signal penetration. So
Okay.
if you're finding that you have like dead spots in your house, going to 2.4 gigahertz can allow the signal to get through walls and stuff a little bit better. That's a trade-off to consider.
Okay. Yeah, a lot of moving pieces.
Well, Rebecca, I don't have a question, but I just wanted to give you a compliment on the presentation. To be honest, I didn't know anything about this topic before we started, and I felt like I could pretty much follow along. I'm definitely gonna have to Google some stuff after this and get a little more information, but I found it easy to follow along, and I thought that you made a topic that could be very dry, very entertaining. It was very funny. I found myself chuckling pretty much every slide, although you couldn't hear me because I was on mute. But yeah, I just want to say thank you for this because I thought it was very, very informative and entertaining as well.
Thank you so much.
Yeah, I concur completely.
Yeah, it was a really good presentation. Yeah, thank you so much for all the information, really.
All right, thank you all. Any other compliments?
You're awesome.
I will drop this presentation in Slack as well. So if you'll want a copy of it, it'll be there.
Yeah. And once I stop the recording, I get the MP4, we'll get it uploaded, and I'll send the link out to everybody on Slack and on Meetup. So if you want to go back through it, I know I probably will. Yeah, but this was great, Rebecca. Thank you so much.
All right. Thank you all.
All right, guys. With that, I mean, I guess we're going to conclude this thing. I'm not going to drop off immediately, so if you want to kind of hang around a little bit, but, obviously people have things to do. So, yeah. And let's see. So, if you drop off in 2 weeks, the STL full stack, right now we don't have a speaker. Hopefully we get something going. We'll be meeting probably back here on this link again. If not, in 4 weeks, we'll do another jSTL something or the other. So, yeah, hope to see you guys here soon, and take care of yourselves. See you guys. I'm going to stop the recording now.